Greetings. We are at the desk now and we would like to start the experiment of Lab 4.1 and then continue with Lab 4.2. In Lab 4.1, I'm going to have a function generator, I'm going to have an oscilloscope and existing components, capacitors and resistors. Now, we have seen this box before. The component we are going to use is 1 kilo. And this one is 1 kilo. So this is the second column, the third component, that's 1 kilo. You can also identify that by the colors of the resistor. It's a fixed resistor. We don't have to use the variable resistors because they usually bring in with themselves some type of noise. This is a capacitor, and in this experiment we are going to use 0.1 microfarad capacitance, microfarad, so it's already 10 minus 6 already given. So 0.1, this is 10 minus 1. If I put it at 1, it's going to be 0. This one is going to be 0.1 basically microfarad. So that's the way I'm going to go. The two red pins are going to be utilized in terms of the two heads, two nodes of the capacitor. So microfarad, 0.1, and these two. Now on top of these and the wires I'm going to use, I need to introduce two new components. One of them is called the function generator. There is a power on button. I'm going to push this in. It has a display, it has a frequency knob. It has a row for the frequency, which takes me to some different values depending on the button I'm going to push. But also I want you to be very conscious about this one. As soon as you turn this on, the middle one is on. This middle one is a triangular waveform, but the waveform we are going to use in this lab is actually going to be a pulse waveform. So I need you to make sure that you have pushed this in. That's going to be a pulse. The frequency, you can change that, as you can see. Well, we are going to be happy with 400 hertz. It's going to give us enough time for the components to get to the steady state response. If it is 407, 398, that's fine. As long as you're around 400 hertz, that's fine. We don't have to worry about duty cycle or offset. We make sure that they are pushed in. This one is the amplitude, and we are going to use that. You can initially set it to maximum, but you can actually start with any value, and eventually you can see if you can read the components properly. That's going to be the output of the function generator. The function generator has a real ground. This is not only a reference node for us, but also it is a real ground, which means all the grounds have to be in one place in this experiment, and in this case all the grounds have to be exactly in this node. Wherever this black one goes, all the ground have to be the same place. This red one is going to actually supply me with the signal I'm going to see. So that's one thing. I'm going to show you the signal in a moment. The second thing is a scope. On top of that, on the left hand side, you have a button. You push this in. It takes a bit of a time to turn on, and it's going to go through a bit of a self-test mode. But there are a few buttons on it. You don't have to worry and panic about the number of buttons and the complexity of the device. It's really not as much complex as one might think. You have the most important button you need to use is AutoSet. So whatever happens, you just put the AutoSet and the signal comes back to you in front of you. You can see that on the scope. So AutoSet is a very friendly key that you can use. Now there are a number of columns. Column 1, channel 1, column 2, channel 2, and then column 3, which is horizontal. On channel 1, I can actually scale it up and down. I can actually move it up and down. So this is a scaling button, and this is up and down shifting the channel 1. This one is going to be vertically. I can scale it, increase it and reduce it, and this one is going to be shifting for me. And then this one is going to expand this horizontally and then shift it horizontally. Let's see what I mean by one of these. This is channel 1. And I want to show you the signal I just talked to you about. Black goes to black. All the black goes to black. If you don't have a black, sometimes it's just yellow, because obviously we the black one was gone and destroyed. So I need to make sure all the black, all the ground go into one noise, right? So this is channel number 1. Black goes into black, ground, and then red goes into red. That's one thing. And then I simply push AutoSet. Let's see what happens. Well, you can see a pulse coming in. This is the pulse. What is this guy? This is noise. You can actually see how it works with this noise. This is a noise that can be actually taken from the air. So this noise could be even as simple as 60 hertz that you have in surrounding environment. So far, I connected channel 1 to the function generator. You can see if I play with this, I can actually change the frequency. As I said, let the frequency be around 400. That's a good one. Don't be obsessed. This one is going to be the amplitude. You can see that I can change the actual amplitude of the incoming signal. But also, you can virtually change the display. When you change the display, it doesn't mean that you have changed the actual signal. So here I would like to go and say, I want to shift this up and down. I can take it down. I can take it up. I can put it in the center, for example, and then I can actually expand this. This is just for my sake, so that I can actually expand it and see it better. Channel 1. Let's get rid of this noise for now. I'm going to push channel 2, and I'm going to get rid of that channel 2. Twice I did channel 2, and the noise is gone, because now I'm focused on channel 1. Take a look at the reading. The reading on this screen, you are going to see, I'm hoping that everything is visible. So let's see if we can have everything in your front. Channel 2 twice. Now I can bring this down if I want to. I can expand this, as I said. But take a look at this reading. This is channel 1 and it says 20 volt. What does this mean? Now, if you take a look at my display, it's very much the same as the paper you might have been using in the past. You can see grids, dotted line, horizontal grids, and you can see vertical grids. Now, how many horizontal grids do you have? 1, 2, 3, 4, 5, 6, 7, 8. I have 8 units. So you can see 8 units everywhere you go. In horizontal, in the vertical domain, every single unit is going to be 20 volts. So this is 1, 2, 3, 4, 5, 6, 7, 8. Every unit times this is going to be the voltage I'm going to read. Now, horizontally, I'm going to see 1 millisecond. So how many units do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 units horizontally. So this is going to be 1 millisecond each unit. Now, if I wanted to read this, you don't have to, but if I wanted to read this properly, I'm going to choose my own reference point. I'm going to shift this up and down. I'm going to make sure, for example, that this one is basically taken. This one is going to be at the place that I can actually rely on. So that's my reference point. So how many units do I have? 1, 2, 3, 4, 5, and a little above. A little above. I would say 5.1 times 20. You've got yourself 5.1 times 20. It's 102 volts. This is the vertical, and that's going to be representing my incoming voltage. So 102 volts. Now horizontally, what do I see? I see 1 unit, and I also see a fraction of a full unit. If I zoom in carefully, I'm going to see, for example, a small bit of it. I'm going to see 1/5 of this unit. So it's going to be 1.2. 1.2 times 1 millisecond, that's going to be 1.2 millisecond. That's the way I read horizontal, that's the way I read vertical, and I have the pleasure of actually shifting this properly, picking up my reference, and so on. Now, you may want to actually choose a reference point somewhere else. This column is at your disposal. You can actually move it, shift it to the left, you can shift it to the right. So that's what I'm going to do. I'm going to go and I'm going to say that's the reference, and I'm going to open it. Okay. As soon as I change the compression rate, it's 500 microsecond now. It's the same signal, nothing has changed. But here I have 2.5. This is more accurate now. 2.5 times 500 microsecond, that's the basically the unit in time that I'm going to see this. 2.5 times 500 microsecond. So you've got yourself vertical, you've got yourself horizontal, you can read this signal. The intention in lab number 4 is to be able to use those scope properly, to use the function generator properly, and move on. Now take a look at this one. Channel number 1, channel number 2, and this horizontal position and AutoSet. Anytime you're not happy, you just come back and you say AutoSet. So that's the way it is. So we know how to use the function generator, we know how to use this. Every oscilloscope actually has a print opportunity. If you have a USB which has maximum 2 gigabyte, it cannot read anything more than 2 gigabyte. If you have a 2 gigabyte maximum USB, you can put it in and simply say print, and what it does, this is a digital oscilloscope, and all the information are going to be saved into this. You can take it home, you can go and have an Excel sheet and basically play with the function and do some analysis over this. There are a few other components and functionality. I'm going to explain that in a moment. So let's go back. I'm going to turn this off for now. I want to make my connections. There is a bit of a correction that I need you guys to remember. For RC, I need you to put this resistor on top. So it's going to be 50 ohm, 1K, 0.1 microfarad, and then connected to the ground. And then the entire intention would be to focus on the resistor that is going to be on top. It's just for the purpose of reducing the noise and making it a lot easier and more accurate reading. So here is my signal. And by the way, this 50 ohm that you see is actually part of this. Take a look at this reading. It's 50 ohm output. 50 ohm is inside. We are not going to put a 50 ohm in this process. So I have a function generator. On function generator, if you remember, the red one is supposed to go, I want to make that more clear. So this is 1K, and okay, this is the modification I'm asking everyone to consider. The 1K is on top, 50 ohm is internal. You have a capacitor, one end of the capacitor goes down to 0. Now, for this resistor, I'm going to monitor, and both sides I'm going to monitor and see what happens. So I need to go from the function generator, the red one. So if you take a look at this, this is what it is. This 2 is going to be available to you. So this one goes to 1K, 1K goes to 0.1 micro, and it comes back to the ground. This is my ground. My ground is one end of the capacitor. Then I'm going to go into 1K. Then I'm going to go from 1K, I'm going to go back into capacitor, and I'm done. So the function generator goes into 1K, it comes back to the capacitor, and the capacitor is set to 0.1 microfarad, and I made the loop complete. So I need you to consider and be aware of the changes I just asked you to do. Now, I want you to be conscious about the 2 ends of the resistor. So this is the 2 ends. Remember, all the ground go, before you start anything, just make sure all the ground go into the same node. So this is one channel, channel number 1, and this is channel number 2, and I want all the ground to go in. Regardless of where the observation points are, make sure all the grounds are there. Make sure the first step is done correctly. Now, channel number 1 is this one. Let's pick it up, channel number 1. Channel number 1 goes into the, for example, this end of resistor and the function generator. So that's this one. Channel number 2 goes into the other end of the resistor. You turn this on. As you can see, my signal is triangle. I'm not supposed to use that. I'm supposed to push this in for the pulse. Now I'm going to do this as an AutoSet. You can see this signal. This is channel number 2. I'm going to actually take this off The first one I took it off. And channel number 2, it's no-brainer. This channel 2, you have a capacitor and it's gone to the ground. This is the VC. And since you want to actually measure a tau through VC, that's why I wanted to make sure this is clean. You can play with channel number 2, you can raise it up, you can take it up, you can choose your own ground and basically open it if you want to. Make sure you have a flat response. This is flat response, this is flat response. Make sure you have a flat response. So let's see. Well, I'm nice. This is going to be fine. My signal is good. I intentionally picked up this as my reference node, and this is a very good signal reaching a steady state. How much is my gap? I need you to have your eyes on this line. 1, 2, 3, 4, 5.2, 5.1. 63% of that. So it's going to be 5.2 times 63%. There would be some values. I don't have calculator to calculate this. And then you find it. So for example, it's going to be 3.4. I'm just making a guess. 1, 2, 3, 4. You find 3.4. You come in and hit the graph. You come down. You read this. That's your time constant. This is supposed to give you a very good reading in terms of the time constant. So please make sure you have this first. Let's go back again and bring in my channel 1. Well, there are 2 different channels, and what I'm going to do, I'm going to put the math mode. You can actually make sure that this is also 20 volts if you like to, but it's going to exceed my limits, so I'm going to actually take it down a bit. So 50-50, that's fine. I'm going to push my math, and I'm going to accept the minus sign. So let's take channel 1 out. This was your original voltage of the capacitor, and this is going to be your derivative. You are going to verify that using the oscilloscope. So you can actually play with this and basically make it better. This is what you just recorded. This is the one you use now, and then this is going to be your related to IC. What is that? This voltage minus this voltage. That's what I created for you. This is the subtraction of channel 2 from channel 1. Whatever it is divided by 1K, that's what you're going to read. You're going to read it properly. You have the basically the math is going to be 50 volts, so it's going to tell you how much it is, and therefore you can calculate this and accordingly tell me how much my IC is. Unfortunately, because of this little thing, you cannot really see exactly what it is, and therefore although theoretically you can find the tau from this graph, the IC graph, it's practically it's going to bring you a number of errors. So basically we are going to rely on this and find the tau and show that it is going to be at some point and then a steady state, and you can actually see it how it works. Take a look. I want to make it smaller. Go up a steady, come down a steady, go up, and so on. And this is going to mimic the IC. IC is equal to C dVc to dt. Now, having said RC design, in RL though, I want you to actually follow exactly what you see on this graph. So let's go back. I'm going to turn off my function generator. I don't want to turn off the scope because a scope turning it off and turning it on, it takes time. It has a self test to do. So I want you to take this off. Again, the intention of those little changes I just mentioned for RC is to make sure you are going to get a good noise-free reading. I'm going to change my capacitor with the inductor. This is inductor. These 2 red pins I'm going to use as my 2 ends of the inductor, and the inductor is supposed to be 0.5 Henry. So that's 0.5 Henry, 0, 0. This is 0.5 Henry. I'm going to use that. Now, if you take a look at my design for the inductor, I'm supposed to go from the function generator first to inductor, then to 1K, and come back. So let's do it. Function generator with the red, go into the inductor first. So I'm going, and it doesn't matter which end you go, just go into the inductor. From the other end of the inductor, you go into 1K, and then from the other end of the 1K, you go to the ground. This is now my ground. Regardless of what I'm going to do, I'm going to make sure that those scopes grounds are all the same. So this is all the same. So that's my scope ground. Okay. Okay. Now, this time, I'm going to follow what the instruction says. Channel 1 goes on top of the inductor. Channel 2 goes on the top, bottom of the inductor. Channel 1, you need to follow and make sure you have channel 1. So channel 1 goes into the place where the inductor and the function generator meet. Channel 2 goes into the other end of the inductor. As simple as that. Nothing more. I'm going to turn this on. I'm going to push this to the pulse generation at this time, and I'm going to start playing with this. You have to put this as AutoSet. Let's start from scratch. That's your signal. So this signal might be too high. I need you to make sure you have a good saturation for this. So that's why I actually reduced the frequency even to 250. 250 is good. I'm just making it. All you have to do is to actually observe the value, the flattening of the response on this. Let's open this. I want you to actually measure this, and that's where the tau is going to be measured. I need you to pick up a good reference point, expand it please, expand it again, you have the room, and then let's put this in, say, I'm going to take it down. Which one is that? This one. Okay, I have room. I'm going to expand this. So I have room. As long as I have room, I need you to be able to make a good signal readout. So that's my reference node. That's my signal. How do I measure my tau? Well, this is my gap. So it's going to be 1, 2, 3, 4, 5.9. 5.9 times 63%. Well, let's make a number. 3.4 again. 1, 2, 3, 4. You come in, you hit the graph, you come down, you read this. That's 250 microsecond per unit now, and then you can see and read how much your tau is. So that's one thing. The second thing is, I would like to see how much is the basically IL is. So let's go, and this time IL would be the one that goes on to this one. So I'm going to put I'm sorry, IL, this one is actually a representative of IL, because V2 minus 0 divided by this, that's what my IL is. This is channel 2. That's the channel 2 that I was just talking about. Now I want to find the voltage across this. My expectation is V is equal to L di to dt. So I need you to put the math in. You have a minus operation. You don't need channel 1 anymore. That's a noise. That's unwanted, it's not a noise. So you can see the signal goes up and you have a simple derivative of it. You want to see it in action, you can actually see it in action. Go up, go down, go up, and as such you have derivative, derivative, derivative. You can plot this accordingly. This is nice and clean. Often we have noise with the inductance, but with the little change we did for both RC and RL, you are going to be safe in terms of recording it. The intention is to record the function, verify that the function in terms of math is going to be following the numbers and everything, and calculate and measure the tau and verify that accordingly. Thank you very much. Talk to you soon.